Well, thank you, Caitlin, and the organizers very much for having me here today, and thank you all for your attention. Most of what Caitlin discussed in that introduction, I'm not going to be talking about today. So I'm currently affiliated with the University of California, Berkeley, where my focus is much more on non-proliferation work and nuclear physics for more applied purposes. Today, I'm going to talk to you about work I did as a PhD student at Michigan State University at the NSCL with Betty Sang. This is work that I mostly did funded by the Stewardship Science Graduate Fellowship, which is an NNSA fellowship managed by the Krell Institute. So I'm going to talk a lot today about transfer reactions and this question of asymmetry dependence of spectroscopic factors. But of course, this story is much larger than just transfer reactions. So I'm going to talk about other topics as well. And fortunately, many of these topics I'm going to discuss have been already brought up in this seminar series. So I'll try to point out the connections anywhere I can. Sorry if I missed anybody's talk, but hopefully this will enable everyone to be kind of caught up and some good discussion afterwards. So the basics: in the independent particle model, we assume that each nucleon moves independently in some mean field, which comes from the interactions of all the other nucleons, and correlations, either short range or long range, like collective excitations, between individual nucleons can disrupt this picture. And one way we can study this is using a quantity called the spectroscopic factor, which tells us in a quantitative way the occupancy of a certain single particle orbital. So the definition here shows an n-1 body wave function and an n body wave function, and then this annihilation operator here, which corresponds to a single particle state with quantum numbers given by p. And the idea is we want to see to what extent basically does this n body wave function look like this n-1 body wave function plus a nucleon in state p. So a long time ago, about 30 years ago, there was an experiment at NICF doing electron-induced knockout reactions, so EE prime P, and showed for lots of different stable targets a substantial reduction in single particle strength compared to the independent particle model picture. So you can see the plot on the right shows the spectroscopic strength, which is the spectroscopic factor normalized by the independent particle or mean field theory maximum. And on the x-axis is the target mass, which basically just shows you the wide range across this reduction, across which this reduction was seen. And pretty consistently, this spectroscopic strength is reduced to about 60 to 70% of what you would expect from the mean field. So this is already quite interesting. And this EE prime P probe is nice, first of all, because it's electromagnetic rather than hadronic. So, in principle, it's more straightforward to model and also can penetrate to the nuclear interior a little bit more easily. But on the other hand, we're interested in the nuclear structure, nuclear reactions community, we're often interested in exotic nuclei. And EE prime P cannot, as of now, or has not reached beyond the value of stability. Furthermore, even if you could reach all these other nuclei, you can't access any particle states. You can only knock out protons, and you can only access whole states from proton removal. So you can't knock out any neutrons. So there are other techniques to study this same phenomenon of spectroscopic strength reduction. One such technique is transfer reactions. So this is where an individual nucleon is transferred from projectile to target or vice versa. And this gives you more flexibility in terms of what isotopes you can study, as well as the individual states that you can access. So for a little while, it looked like there was a discrepancy between the spectroscopic factors coming from transfer and those coming from electron-induced knockout, proton knockout. So Kramer et al. In 2001 showed that with a consistent and appropriate analysis methodology for, in this case, D helium-3 data, you can get consistent spectroscopic factors, consistent reduction from mean field when compared to the EE prime P. And I'm going to talk more about an analysis methodology later on. So transfer reactions allow for useful studies in nuclear structure that we wouldn't otherwise be able to do with EE prime P. And one example is shown here on the right. So on the y-axis here, I should have mentioned that on this left plot, the x-axis is excitation energy. These are several different states in calcium, for which you can see the ratio of the D helium-3 spectroscopic factors in the EE prime P are mostly around 1. On the right plot, the y-axis is the experimentally determined spectroscopic factors from transfer reactions, and on the x-axis is a shell model calculation. So this is doing, like I showed on the previous slide, this overlap of wave functions to calculate a theoretical spectroscopic factor. And these 4 panels correspond to 4 different shell model calculations using different bases and different interactions. And a slope of 1 would correspond to perfect agreement between the experiment and the nuclear structure theory. What we can see is that 3 out of 4 of these slopes are around 0.7 or 0.75, indicating that the structure model is not doing a good job of matching the data. So the one that does the best is this upper left panel, which has the calcium-40 core, so it's including a full PF shell basis and using this GXPF1A interaction. So basically, you're using transfer reaction spectroscopic factors to discriminate among different shell model calculations, different bases and different interactions. So it's a useful tool. Now in this talk, I'm going to focus on a type of transfer reaction called single neutron pickup, or PD. So the formalism I'm going to use today when I'm talking about transfer reactions is basically assuming a 3-body system. So you can see here on the right, this is a figure adapted from the excellent textbook by Thompson and Nunez. You have a proton approaching a system A, which consists of a core B bound to a neutron N, and then a transfer happens, so you end up with a deuteron and B. And the way this is often done is using the distorted wave Born approximation, in which you write down your Lippmann-Schwinger equation, which is an implicit series, and then split the potential into 2 separate components, U1 and U2, the latter of which you treat as a perturbation on U1. So you can write what's called the 2 potential formula, which tells you your T matrix that you're interested in due to both of these potentials can be written as the T matrix due to just U1 plus the T matrix due to the effects of U2 on U1. So using a distorted wave with U1 to calculate the effect of U2. And so what we can do when we write down what these potentials look like, we can choose two different frameworks to write things down in, either a prior framework before the transfer happens, or after the transfer happens, what's called the post framework. And so both of them have some kinetic terms, entrance or exit potentials respectively, a term describing the bound state of the neutron, whether to B or to the proton, and then an interaction term, VI or VF. And when we look at the interaction terms, we can see that in the prior formalism, we conveniently have this UPB minus the entrance potential. So basically, we're looking at the potential between the proton and B and the potential between proton and A. For sufficiently large systems, these two are going to be very close to each other, and we can assume that they cancel out. And what we're left with is just the potential between the neutron and proton, which of course we have a lot more data for and understand better than the nucleon-nucleus optical potentials. So this is quite convenient. So we're going to choose to work in the prior formalism. And for a single-step DWBA approach, we can choose a spherical U1, which means that no angular momentum can be transferred by U because of U1, and therefore that no nucleon transfer can happen because of U1. So we already know that the T matrix on account of U1 is already going to go to 0. So now our T matrix from DWBA can be just written with this one term that has this distorted wave, or these distorted waves chi, that include the effects of U1 folded in with U2 in the middle. So for our case, going from a specific entrance channel alpha to some exit channel beta, we end up with this down here on the lower right. We also make a variety of approximations. So first of all, the adiabatic distorted wave approximation, or ADWA, basically what we do is assume that the internal motion of the neutron and proton in the deuteron is slow compared to the motion of the deuteron. So that allows us to model the deuteron target system as neutron target and proton target systems that we then combine together, as you can see in this equation up here. This is nice for two reasons. One is that, you know, typically we have a more empirical basis for the neutron target and proton target potentials, but also the deuteron has a binding energy of about 2.2 MeV, so it's often going to break up. And so this approach introduced by Johnson and Soper allows us to take that deuteron breakup into account when we calculate our transfer reaction cross sections. Nunez and Deltuva did a benchmarking of the ADWA compared to exact Faddeev calculations for a few systems at low energies with low angular momentum transfer, but the ADWA performed quite well, I think within 10% of the exact calculations. Another assumption we make is shown by the second equation, which is the local energy approximation. So if you look up here in the potential for the ADWA, we assume this kind of zero range strength between the neutron and proton be zero. The local energy approximation basically just adds a first order correction onto that, which depends on some effective radius given by beta and the wave number of the deuteron given by KB. Lastly, the last important approximation we make is in terms of the non-locality in the system. So our approach is to use Perret-Buck, which has been around since the 60s. Basically, you take your potential and there's this correction H, which basically just applies a Gaussian adjustment to your local potential U to include effects of non-locality. I'm going to talk about this more in later slides, so I'm going to defer any more discussion for right now. So another probe that you can use is the knockout reaction. So typically when I say knockout reactions in this talk, I'm referring to knockout of a single nucleon induced by a beryllium target or sometimes a carbon target. And so what we can do with knockout reactions at intermediate energies is have a very sensitive probe for the shell model for nuclear structure at really high levels of asymmetry. In other words, really low beam rates. This allows us nuclei that we would not otherwise be able to access even with transfer reactions. And so it's possible, because in principle this is a simple reaction mechanism with an iconal approximation, you can separate contributions by detecting everything in complete kinematics, as you can see from this paper by Bazan et al. On the right. You can see for the proton, the green line here, they were able to model this quite well by splitting up into inelastic components and elastic components for both of these reactions on carbon 9 and boron 8. So this allows you to constrain the reaction mechanism and make sure that you measure what you think you're measuring. So once knockout allowed all of these new systems to be available, people started to explore that. And so there were some measurements in boron 8 and carbon 9 by Enders et al. That showed for these really loosely bound nucleons, there was very little reduction compared to the shell model, less so than in the case of stable nuclei measured with EE prime P. And on the other end, when you're looking at deeply bound nucleons, a measurement of argon-32 by Gada and collaborators showed a massive amount of quenching. The experimental cross-section was only about 25% of the theoretical expectation. And this is communicated here in a really nice plot on the right from a seminal review or seminal systematic paper by Tosteven and Gada from 2014. On the x-axis is a quantity delta S, which I'm going to be using a lot today, which is the difference in separation energies. So for neutron removal, it's Sn minus Sp, and proton removal, vice versa. And basically, it's communicating how bound is the specific nucleon that's being removed from the nucleus. And on the y-axis is a quantity called the reduction factor. Basically, you can think about this as spectroscopic strength. It's the experimentally determined, in this case, cross-section or spectroscopic factor compared to what you would expect from the theory. And so what we can see here is the EE prime P data in black, delta S near zero, because we know that those nuclei are near stability. So not very asymmetric. And then the red and blue correspond to neutron and proton removal respectively. And you can see here that for both cases, when we're removing loosely bound nucleons, we get much higher, we capture the spectroscopic strength much better than in the case of deeply bound nucleons. So I mentioned argon-32, but there's all of these other systems that have been studied with this knockout technique. So this is well established, this strong asymmetry dependence or quenching of reduction factors in using knockout. So when we look at transfer and try to spread out to higher asymmetry with transfer, we don't see the same strong quenching. So first of all, when you look close to stability, you can see the paper on this left is again delta S versus FQ, which is what they call their quenching factor, reduction factor. You can see that for lots of different proton and neutron transfers, this corresponds to lots of different techniques, so PD, D-helium-3, et cetera, and lots of different angular momentum exchanges. There is no evidence, at least between delta S -10 to 5, of strong asymmetry dependence. When you go to higher asymmetry, there have been some measurements, in particular on argon isotopes by Lee et al., and by oxygen isotopes by Flavigny and collaborators, and you can see those results on the right. So the oxygen isotopes are shown in red, and you can see this is now going from about -20 to 20 or so, and the argon isotopes are shown in black. Some of these measurements in between are from very old data sets, which is why the uncertainties are so high and there's a little bit of scatter, but still there's no evidence of a very strong asymmetry dependence. It's weak dependence or perhaps no dependence. It's kind of hard to tell from just this data. So it's a little bit easier to make this comparison if we focus on a single isotopic chain. So we're going to look at the argon chain today, and we'll see clear evidence of discrepancy between transfer and knockout. So on the plot here on the right shows again delta S on the x-axis. We're talking about neutron removal, so that's Sn minus Sp, and this reduction factor on the y-axis, which is the ratio of experimentally determined spectroscopic factor and the structure expectation. In blue is the knockout data on argon isotopes. I mentioned the argon-32 measurement earlier. There's also a few other argon-46 and argon-34 measurements for neutron knockout done by the same group at the NSCL that did the argon-32. And in red are the argon transfer measurements I mentioned on the previous slide. So these are the measurements that were done by the group that did this publication. So the older measurements in between are cut out. And you can see that there is either no or weak asymmetry dependence. And regardless, it's a very different looking trend than what we see with the knockout, even though for the really loosely bound nucleons, the spectroscopic factors seem to agree. So the question is why? Obviously, this is important because these two techniques are giving us different answers as to what's happening from a structure perspective. So aside from that, why could there possibly be a difference? One is that there could be a problem with the experiments, with the data points that I'm showing. I think this is unlikely just because these trends have been pretty well established with each technique by different groups, different measurements on different systems. Another possibility is a problem with the reaction model. This is possible. This is something that we need to take into account or need to think about at least. Another possibility brought forward by Nunez et al. In 2011 is that if you look at just the argon data, the uncertainties are actually too large to say. They claim that the reaction model uncertainties, or the uncertainties because of the reaction model, are significantly underestimated, and that if you make these argon error bars larger, now all of a sudden you can't clearly rule out that the transfer, you can't clearly claim that there's a discrepancy between transfer and knockout. I again claim this is unlikely simply because, again, there's different experiments by different groups that are showing these trends, and I'll talk about later, there's also different techniques that are weighing in on this now beyond transfer and knockout. So back to the reaction model, perhaps one of the techniques that we're using here is broken. So perhaps the transfer model is broken. So let's try to break it and see what happens. So the transfer measurement in red was done at 33 MeV per nucleon, which is a typical energy for a transfer reaction. It's where cross sections are highest. Typically, if you want to do a transfer measurement, that's a nice place to be. Whereas I mentioned earlier, the knockout uses intermediate energy. You want to be able to be at a high enough energy to apply the iconal approximation. So this is a pretty significant difference in beam energy between these two approaches. So what we can do is try to run the transfer experiment at a knockout like beam energy, in this case of 70 MeV per nucleon. So the idea is if the transfer mechanism is not giving consistent results, then that perhaps points to specific problems in the reaction model that we're using to extract these spectroscopic factors. So I'm going to talk about the experiment that we did for these high energy transfer reaction measurements. So this is a cartoon of our experimental setup, which took place at the National Superconducting Cyclotron Lab. We measured both argon-34 and argon-46 PD at 70 MeV per nucleon. There were three main detector systems that we used. The microchannel plate, or MCPs, were placed upstream from the target and allowed us to track the beam before it hit the target. First of all, we need this to normalize how much beam is actually making it to the target. We're calculating a cross section. We need a denominator for that. We also used it to track the position of the beam before it impinged on the target in order to give us better resolution when we reconstruct the excitation of the heavy recoil, either argon-33 or argon-45. You can see here on the lower left what the calibration for the MCPs looked like. Basically, we just stuck a brass mask in the beam line, and we saw these, we can reconstruct the mask pattern of well-defined holes to do our calibration. We also measure the deuteron coming out of the transfer reaction, coming out of the PD, using the high resolution array, or HIRA, which is a set of silicon cesium iodide telescopes. We had a single-sided thin silicon, then a much thicker double-sided silicon, and then an array of 4 cesium iodide crystals. You can see here on the right a particle identification plot, in this case between the thick double-sided silicon and the cesium iodide, and you see that we can clearly separate out the deuterons in order to gate on the PD reaction channels. Lastly, we use the S800 spectrometer to identify the heavy recoil, using kind of the standard approaches for the S800, looking at the energy loss in the ionization chamber, and also the time of flight at which the recoil arrives at the S800 focal plane. And in this case, this is the PID plot for the argon-45 beam setting, gated on deuterons and HIRA. We get, the kind of classic blob structure. We allow the unreacted beam to pass through the S800, which then allows us to plant a flag in all these different blobs so we know what's what, and then we can easily identify the residue that we're interested in this case, argon-45. So the important thing about this slide is that we're measuring PD with complete kinematics. Everything that's coming out of the transfer, we're measuring. I want to talk quickly about some calibrations we did. We did some pretty detailed characterizations of these HIRA detectors. So one that we did was use an irradiated pin source inserted between these two silicon detectors in order to calibrate this thicker silicon detector. The idea is that, first of all, we don't want to have to take apart our detectors to do calibrations because obviously then the calibration is not necessarily valid. Secondly, we know that on this double-sided, or on this DSST, there's a dead layer. And we'd ideally like to know how thick that dead layer is because it's going to affect our calibration. And so we had this pin source with a spectrum from lead-212. You can see the alpha energies here in this plot. And we have a position-sensitive silicon detector. So when we put this pin source very, very close to the surface of the silicon detector, as shown in this cartoon here, we get the particles passing through the dead layer at very large angles given by theta. And so we can measure the thickness of this dead layer T. So on this plot on the upper right, you can see the energy of the alpha particle as a function of 1 over cosine of this angle theta. And you can see that it conforms exactly with what we would expect from geometry. And we have 2 alpha particles here, so we can actually do 2 different measurements of the dead layer, and that's what's shown on the lower right. So the dead layer thickness on the y-axis for all the different detectors on the x-axis. You can see they all cluster around 0.6 microns, which is around what the manufacturer had told us they expected. We also, in order to calibrate the cesium iodides, did detailed characterizations of the thickness of this double-sided silicon detector. So basically, in order to calibrate the cesium iodide data, we used energy loss tables as well as the calibrated energy in the E detector to understand or calibrate the response in the cesium iodide detector. If we know how much energy a particle deposits in the silicon, we can tell how much is left over in the cesium iodide. But when you do this calculation, it's very sensitive to the specific detector thickness. So what we did was we used some high energy elastic scattering data. So these are, beams that are energetic enough to blow right through the silicon. And we basically compared that to energy loss calculations with lots of different detector thicknesses. So the nominal thickness of these detectors is 1500 microns. So we varied that thickness from 1400 to 1600 microns. You can see here on this plot on the bottom, which shows the calculated cesium iodide energy versus the raw cesium iodide energy. And the thickness that gives us the best fit or the best agreement between the elastic scattering points in blue and these open circles that correspond to the energy loss points is what we determined to be the silicon detector thickness. And on the right, you can see here that actually what we measure corresponds quite closely with what the manufacturer measured. So this is the measured thickness on the y-axis and manufacturer nominal thickness on the x-axis. Which is nice, but you can see how much they differ from the assumed 1500 microns. Anyways, back to the experiment. So here I show the excitation energy spectra for both the argon-33 and argon-45 recoils for the ground state. So this allows us to gate on the reaction channel we're interested in, which is the ground state to ground state PD. On the left is the argon-33 excitation energy spectrum, which is pretty easy to deal with. The first excited state isn't until about 1.359 MeV. So we have this very prominent ground state peak. So we can very easily gate on this, integrate it to get our angular distribution. The argon-45 case was a little bit more complicated because we have a excited state, a P3 halves excited state at low energy at 542 keV. At forward angles, we found that we can tease out the contribution from this peak. This is where our experimental uncertainty is highest, and also where the cross-section for that first excited state is highest. And so we can fit the spectrum that we get with multiple Gaussians, setting the widths to experimental uncertainty that we determined from our data and from simulations. And you can see here that the means that we get for these individual Gaussians are about where we would expect them to be for the ground state and the first excited state. So now this gives us constant confidence that we're properly isolating and studying the first excited state when we make our angular distribution. So after we have these excitation energy spectra that we get with, energy reconstructions with HIRA, gating on the S800, we can now gate on the reaction channels that we want. We can normalize using data from the MCPs to get differential cross sections as a function of angle in the center of mass. And that's what I show here. So for both argon-34 PD and argon-46 PD. So I'm showing reaction calculations here. I ask you to be patient as I will talk more about them in the next slide. What I want you to see for now is that the shapes of the reaction calculations shown in different green and red lines match well with the shape of the normalized differential cross sections for both argon-34 PD into the ground state and for argon-46 PD. So the argon-46 PD is again a little bit more complicated because we have this contribution from this P3 halves excited state. However, like I said, we are able to separate that out. The cross section points are shown in blue and black. The blue points correspond to what we use to actually do the spectroscopic factor extraction, which is just a straightforward chi-square minimization using the most forward angle peak, even though that peak in argon-46 PD is quite weak. So here we use those first 6 points, and on the right we use the first 5 points. So in this way we were able to extract spectroscopic factors, and because the calculations and the data match well in terms of the shape, we're confident that these are reasonable numbers. And I'll talk about the specific numbers in a moment. First, I want to fulfill my promise of talking about the reaction calculation. So like I talked about earlier, this is all using ADWA. We use the 2FNR code for all the calculations as discussed before, and there's 2 separate approaches that we use. One is using the Chapel Hill 89 global optical model, which is parametrized across a fit to lots of different reaction data from lots of different systems, and uses just a conventional Wood-Saxon bound state potential. The other approach is using the JLM optical model with Hartree-Fock calculated nucleon densities. So this is a microscopic approach. So we're calculating for a specific system rather than interpolating or extrapolating from a fit, as in the previous case, what the potential should be in this specific case. So we used Hartree-Fock calculations with SKX skirm parameterizations for these individual systems. And the geometries were determined by basically varying this, the radius parameter of the geometry to match the root mean square radius from the Hartree-Fock calculation of the specific orbital that we're interested in. And this process is described much more in detail by this work by Jenny Lee, Jeff Tosteven, and collaborators from 2006. So these approaches differ, as you can see on the right. So the JLM approach has a larger cross-section than the Chapel Hill 89 approach. And this is probably just because of the different bound state geometries. Like I said, we're varying this radius parameter and we're making it larger than the standard value that you'd use for the Wood-Saxon and the Chapel Hill 89. But they not only agree on the shape, as I'll show you in a moment, they also agree on the asymmetry trend. So the message here, and kind of the central message of all of Jenny Lee's work from her PhD thesis, is that as long as you have a consistent and systematic approach, the asymmetry dependence is going to be invariant regardless of what optical model you choose. So, okay, in terms of non-locality, I said that I would bring this back up again. The physics is, of course, non-local. There's anti-symmetrization of the wave function. You couple to other reaction channels. So the question is Pare-Buck enough to actually take this into account? So there's a nice paper from Deltuva from several years ago, the plots of which are shown on the right. So center of mass angle versus cross section. So for different systems, you can see that the local optical potential using Pare-Buck does not match the data as well as the non-local optical potential. And there's some discrepancy between the two. And this is well established. But of course, if you want to take into account non-locality exactly, you're going to have some problems because that's pretty hard to do. So you have to balance between including the actual physics and a practical application if you're interested in studying these rare isotopes. So there was some interesting work in recent years by Timofeyev and collaborators who basically suggested that you can use the local potential and add a shift to the energy at which you actually evaluate that potential rather than the standard deuteron energy divided by 2. And then you can take into account non-locality. And this basically is taking into account the relative momentum between the neutron and proton and the deuteron at really short range. So an issue with that shown by Luke Titus in his PhD thesis with Filomena Nunes at MSU, is that the energy shift does not always improve the description, the naive local description, compared to the exact non-local treatment. So he calculated the non-local cross sections for several different systems and compared just a standard Chapel Hill 89 approach to a Chapel Hill 89 approach with this energy shift. And you can see sometimes, like in this panel over here, panel C, which shows lead 208, the blue going to green, which is adding this energy shift, improves the description at forward angles of this cross section. But in calcium 40, you do move qualitatively towards the non-local distribution, but the green kind of overshoots the mark. And then lastly, for oxygen 16, it actually seems to move in the wrong direction, going from blue to green compared to the exact non-local. So because of this, and also because we wanted to be able to compare to the previous work of Lee et al. That just used a simple Pare-Buck, that's what we did as well. So this is a really active field, lots of interesting work happening here. It was just a little bit outside of our scope to really include anything more complicated. One question, it's now established by Luke and others that non-locality can significantly influence an individual cross-section. So an individual spectroscopic factor can change by a huge amount. But it's unknown, as far as I know, what the asymmetry dependence of that is. So these non-local calculations as a function of asymmetry would be really interesting to see. Okay, so now we can compare with the knockout and with the low energy transfer. And on the left is the reduction factor versus delta S for the JLM plus Hartree-Fock. And on the right is the same thing for the Chapel Hill 89. And you can see that in both approaches, the present work given by red stars agrees with the lower energy measurement, 33 MeV per nucleon, the green points within uncertainty. And furthermore, the asymmetry dependence for both of those individual transfer measurements with both of these approaches is weaker than what you observe with the beryllium-induced knockout. And you can see that in inset plots for both of these, the slope parameters of these linear best fits. So of course now the story is much bigger than just for a knockout. There's approach, which is quasi-free. So this uses really high energies and proton targets, which basically, in principle allows you to probe the interior better than with an intermediate energy and with non-structuralist targets, so to speak. And so the first measurement to come out was by Attar and collaborators from the R3B collaboration. They studied a bunch of oxygen isotopes, and you can see the results here compared to this gray band, which corresponds to the argon systematics by Tosteven and Gada I showed earlier. And on the right is results from Tuan Phuc et al. And you can see he looked at lots of different quasi-free studies. And again, the blue line or the blue band here corresponds to the knockout systematics. And again, there's discrepancy between the P2P results and the PPN results, which tend to show weak asymmetry dependence as opposed to the strong quenching seen by knockout. And so I'm not going to go into detail here. We just had an excellent talk on Tuesday, and I encourage you to go look at that by Tuan Phuc to understand better what's happening in this space. There's also approaches from a structure perspective. We can calculate what we would expect to see from including lots of different structure to see if we observe this quenching. So there's a coupled cluster calculation from Jensen and collaborators that tries to explicitly couple to the continuum, which basically results in many body correlations that end up reducing the spectroscopic factors. You can see here on the left what a big impact those have. Sorry, the brackets kind of got displaced for some reason, but these top two sets of points correspond to Hartree-Fock calculation, or to structure calculations with just normal Hartree-Fock, so no coupling to the continuum. Whereas the bottom, you do have this coupling to the continuum, and you can see that the black and red points have a much stronger asymmetry dependence than, or rather, a much stronger reduction as a function of the oxygen isotope number as a function of A than the gray points. And you can see this plotted as a function of delta S on the right for oxygen isotopes with both proton and neutron removal. So looking at this, it kind of seems like, okay, maybe the quenching is actually quite strong, but if you look closely, the asymmetry dependence, which is there in the calculations, of course, but is more closely matched by the weak dependence that you see from transfer and the quasi-free measurements. So you can see here the green box around Jensen et al. Overlaid onto the systematics of Gada and of Tosteven and Gada. The red line is from the fits I showed a few slides ago. So you can see that the red and the green match more closely than what we get from the systematics. But it's important to say that there is now a clear case being built for asymmetry dependence. So it's perhaps not as strong as the knockout data initially shows, but it seems to be there. We can look at other theoretical approaches like the dispersive optical model. So they used elastic scattering data on a variety of calcium isotopes to fit their DOM, and argue that really in terms of asymmetry dependence, the most important part is this imaginary surface potential. And they included two different asymmetry terms, one weaker and one stronger, to see what happens. And you can see that on the right. So here's the surface, imaginary surface potential. And here are the two asymmetry terms. The top one, they use a similar term for protons and neutrons. In the bottom one, they use the n-z over a for the protons and 0 for the neutrons, arguing that for the proton case, this is much more experimentally established. And what they see when they compare to the spectroscopic reductions from transfer reactions shown in this bottom plot here is that the dark or the black points, filled in points, corresponding to the second weaker asymmetry dependence agree much better with the data than the open points, which correspond to this stronger D1 asymmetry dependence. Also, when you look at the shape of this imaginary potential, shown here on the lower right for the stronger asymmetry dependence, what they indicate is that you end up with a negative potential. And because the volume term is around 0 in this case, you end up with a negative imaginary potential, resulting in what the authors call unphysical neutron production. So neutrons coming out of nowhere. So for these two reasons, they rule out this stronger asymmetry dependence for the DOM. There's even more structure approaches as well. So there's two different self-consistent green function or SCGF approaches that both show weak quenching. One is by Barbieri and collaborators that account to coupling to collective excitations. And they argue that the long range correlations are more important to this asymmetry dependence than short range. But again, they are showing a weak asymmetry dependence. The dependence seems to be there. And Cipollone and collaborators added in some chiral 3 nucleon forces, which are plotted here as a function of proton and neutron separation energies, which same with the previous plot. And they found that this, including these 3 nucleon forces, had actually little impact on that asymmetry dependence. The structure calculation with the strongest asymmetry dependence is from Timofeyev, who proposed an inhomogeneous approach, which basically accounts for shell orbitals that are typically excluded. And she finds a stronger asymmetry dependence than any other theoretical technique, which you can see here. Now, I'm showing you lots of plots of basically spectroscopic strength on the y-axis and the binding of the nucleon on the x-axis. And it's like I showed with the Jensen slide a little while ago, it's kind of hard to make specific determinations based on that. Just looking at these different plots. They all have different axes, lots of different data points. So what we can do, each of these different plots, and look at what I did before with just the transfer and knockout, but now we can look at lots of different techniques, both experiment and theory. And so that's what this plot on the right here is. Each of these different columns correspond to different techniques to measure asymmetry dependence. On the left, you have this blue band, which comes from the knockout systematics by Tosten and Ngata. The argon, or the slope just from the argon isotopes, is shown by this blue triangle. These EE'P bands are presented, with the caveat that they're only the points are only near stability. So delta S is going to be very close to 0. There's going to be lots of fluctuation in the slope that comes out, and so that's what you see here by two sets of data, one from Lapicus and one from Kramer. But neither of them is quite as strong as what is observed in the systematics of Tosten and Ngata. Then we have the transfer band. So these are 3 different transfer reaction compilations. The one on the left is a recent one from Xu et al. The one in the middle is a compilation by Jenny Lee, which also includes the data that I've talked about today because it uses the same analysis methodology as she used for her compilation. And lastly, this last band is from Flavigny et al., the work I talked about earlier with the oxygen isotopes. Again, I pull out just the argon measurements, which are a combination of both my work and Jenny Lee's lower energy measurements. And then you have the PPN column. So this includes 4 separate recent studies of PPN asymmetry dependence. So listed here. And they use different analysis approaches. They include slightly different sets of data, although there is a lot of overlap, mostly in mostly oxygen isotopes, but also some carbon and nitrogen. And then lastly, the last column is the structure theory that I've been spent the last few slides talking about. And what you can see across all these 4 columns is a consistent picture painted of non-zero weak asymmetry dependence. I mentioned before the inhomogeneous approach had the strongest asymmetry dependence out of any of the theory calculations. And you can see that it's about a negative 0.01, still significantly weaker than what we get from the knockout. So one question I want to address, because it comes up a lot recently, is about short range correlations. So there's been some really cool work in the electron scattering world recently. They've had lots of interesting results. Here's one in particular from Duer et al., where they basically show that as your N over Z fraction goes up, more and more momentum, more and more of your protons have high momentum. So basically your protons, as you can see here in this inset in the upper left, protons get shoved into this high momentum tail above the Fermi energy, which is of course going to affect, you would expect it to affect the single particle strength below the Fermi momentum. And so the question is, okay, this clearly provides some more physics motivation that there is an asymmetry effect of these correlations, but to what extent? We've already kind of talked about, or I've already mentioned that there's clear evidence for asymmetry dependence. It's kind of just a matter of how much. So Pascalis and collaborators did a phenomenological approach where they used this data from Dewar to include the effects of these high momentum short range correlations. And they ended up with this band here, which you can see in pink on the right. And I overlay that with the argon data from our work, as well as from the beryllium-induced knockout. And you can see here that even when we include these dramatic short-range correlation results that have been popping up recently, we still get a trend that's more similar or more weak than what we observe with knockout. Now, I didn't put this on the previous plot because they actually treat differently loosely bound nucleons and deeply bound nucleons. So I didn't want to just do a linear fit to that. But you can still see here that it's the same story. So we can brainstorm as to what's happening with the knockout that we get this strong asymmetry dependence that nobody else sees. One possible reason is the iconal approach not being appropriate. So we have these intermediate energies, which seem to be pretty high, but when we have a really deeply bound system, that assumption may no longer be good. So a great example of that was previously discussed by Bonaccorso in her talk, not June 23rd, sorry, that is the wrong date. When I send these slides around, or when I post them on the website, I'll put the right date there. And you can see here, especially for this oxygen 14 case, the dotted line represents the iconal expectation, and the data just is very different. You can see some low momentum tails in other data sets, but the point is when we have a loosely bound proton being knocked out, we get nice agreement with the iconal, but when we're knocking out this really deeply bound neutron, we do not. So that is perhaps indicative of the reaction mechanism not being sufficient. There's also some results here from Grenier et al., which again show these low momentum tails that they fit by basically adding the iconal with a Gaussian correction. But interestingly, it's not always the case. I mean, if we look at the argon 32 measurement that I've talked about a few times now, there's obviously not that much statistics because it's a very asymmetric system, and maybe there's something happening here at the peak, but you don't see the really blatant tails that you observe in the other cases. So it's I encourage you to look at Bonaccorso's talk for more details. Another suggestion that's been made is core excitations. So Luchard et al. Looked at indirect effects with an intranuclear cascade model, and basically posited whether the trajectory of the projectile can be influenced by the target, or maybe there's interplay between the shell structure of the projectile and the reaction mechanism. And the results are shown here on the right for different beryllium-induced knockout systems. The purple points correspond to experimentally measured cross-sections. The bands, either the striped bands, either in blue or in red, correspond to cross-sections with this intranuclear cascade model approach, or with the Glauber approach, which is just the iconal. And you can see here that you get so we can look here, for instance, at argon 32, we get a large difference when we look at the Glauber approach and when we use this cascade model. And furthermore, you would see that if you took the cascade model as your theoretical value, you would get much attenuated reduction compared to the huge reduction you get comparing to the iconal theory. The triangles are there to show the energy dependence, to show basically that how the expectations change as a function of energy. But the message is really the difference between the blue and the red bands. So to conclude, there's clear evidence, both theoretically and experimentally, for asymmetry dependence of spectroscopic factors or quenching. Now, this was first seen by the knockout folks. And so I think it's important to say that, you know, the asymmetry dependence or the quenching observed in knockout, that, you know, is the reason everyone else started studying this to some extent. Although the magnitude of what you see in knockout still seems to disagree with most other theoretical and experimental evidence. But the message is still consistent that there is an asymmetry dependence, which is already interesting. So I talked about some PD reactions at 70 MeV per nucleon, and they agreed with the results at 33 MeV per nucleon. So this is interesting because it provides evidence that the transfer reaction mechanism is consistent across energies, so that we can use transfer reaction at higher beam energies where we can access potentially more asymmetric systems. So obviously moving forward, there's a lot of theoretical work that's important. So I talked about the non-locality already. Something else I didn't even mention, but is still very important, is uncertainty quantification. There have been 2 talks in this series talking about uncertainty quantification by Amy Lavelle and by Katakura Rios that I encourage you to check out. The effects of core excitations and the distorted momentum distributions I just discussed. So again, there's the Bonacorso talk, which talks about these non-iconal effects. So this new data from experimental approaches like PPN, of which, you know, it seems like there's more data coming out every week, which is great. That's important to continue to constrain this asymmetry dependence. There's also the possibility of electron scattering on unstable isotopes. So this is capabilities that are being developed in Japan and Germany, which you can read about here. And there's still, you know, this eliminates basically one of the 3 drawbacks of electron scattering, but would still be really interesting to look at proton knockout compared to these other techniques. For the knockout technique, more exclusive data would be helpful just to better understand any contribution from indirect processes. So this is like the Bazan paper I showed earlier. And then transfer data, there's more still needed at extreme asymmetry, preferably for similar systems as the knockout, so you can make more detailed comparisons. Like I said before, higher beam energies should be okay because we have evidence that this probe is consistent across a wide energy range, as long as you take this systematic and consistent analysis approach. So lastly, I want to acknowledge the funding that I had during graduate school. Of course, my PhD advisor, Betty Sang, and then our group at MSU that helped with the experiment. There was a lot of collaboration from outside MSU. I especially want to thank Jenny Lee and Andy Rogers, who helped a lot with the experiment. Again, the Stewardship Science Graduate Fellowship was really important for me to do any of this work. And if anyone has questions about that fellowship, I'm happy to talk about it over email. And thank you. I'm happy to take any questions.